This is Mrs. Palmerquay with a short video to point out the things that you should review before you sit down to take the second quarterly test. The first thing you need to go over are the types of chemical reactions, and I am asking you to know all 5 types: the formation, decomposition, and combustion that are covered by the book, and also the single and double replacement reactions that I covered in the videos. Just to use generic formulas, a formation reaction, remember you start with 2 elements or simple compounds, and they combine together to give you something new and more complex. A decomposition can be thought of as the reverse of a formation reaction. You're starting with a complex compound and it is breaking down into its individual elements or into simpler compounds. A single replacement reaction concerns a compound plus some new element. This happens with metals, and basically the one metal will kick the other one out, and so you're left with a different compound and an element. In a double replacement reaction, you're starting with 2 compounds and they are switching partners. And so we have AB plus CD, and we'll end up with AD plus CB. And then finally, in a combustion reaction, you have something containing carbon to some amount, we'll just say N, and hydrogen to M amount, and that will combine with oxygen. Oxygen is the key reactant in combustion reactions, and you will form things like carbon dioxide and water, and if it's incomplete combustion, you'll have carbon monoxide or solid carbon or hydrogen gas. But the fact that oxygen and something containing carbon and hydrogen are on the reactant sides are key identifiers for a combustion reaction. I will ask you to evaluate equations that I've given you, and also to write some new ones, balanced of course, from the word equations. And so you still have to remember what the formulas are for the elements that are required and how to make compounds out of that when I'm giving you just a word equation. Stoichiometry is a considerable part of the test, so you need to be comfortable with how to figure out problems when you are converting real-life practical problems. How much will be made given a balanced equation when you're having to go from grams through moles and mole ratios to figure out the grams of the other substance you're investigating. So to just do a simple one, we've got a reaction for sodium nitrate decomposes into sodium nitrite and oxygen gas. So this equation is given to you along with the information that if you want to make 1.5 grams of oxygen, well, how much sodium nitrate do you need in order to accomplish that? I suggest that you make this little table containing all of your key information. First of all, what are we looking at? Well, we're looking at sodium nitrate. Didn't quite give myself enough room here. Sodium nitrate and oxygen. You look at the balanced chemical reaction for the mole ratios. What are the relationship between the coefficients in front of the 2 things that you're investigating? So it's a 2-to-1 relationship between the sodium nitrate and the oxygen. Then you look at the molar mass. Of course, oxygen, each oxygen is 16. I hope you've started to get that. So it's 32 grams per mole for molar mass of oxygen. You'd have to go and add up everything, add up the amount of sodium plus nitrogen plus 3 oxygen. Just trust me, it's 85 grams, going back to your periodic table, to figure out the molar mass. And then the last 2 blocks on your little table refer to the moles that you are working with in this problem and the grams that you are working with. And so we know we've got 1.5 grams of oxygen, and so the first thing we want to figure out is moles, because you always have to go through the moles, so you start by focusing on the moles. So if we've got 1.5 grams and we know that our molar mass is 32 grams per mole, we can do a math calculation to figure out that we've got 0.0469 moles of oxygen. So that would go into here, 0.0469. And since our mole ratio, for every 1 mole of oxygen we get 2 moles of the sodium nitrate, then we just double that amount to say how many moles of sodium nitrate corresponds to this amount of oxygen. So that would be 0.0938 if we just doubled 0.0469. So then we are ready to fill in this last block, because once we know how many moles we need and we know what the molar mass is, then we can just multiply these two together. So 85 grams times the number of moles that we need in order to make that much oxygen, which was 0.0938. You multiply those two things together and you end up with 7.97 grams, or in significant figures, this is just 8.0 grams because we only have two significant figures we're starting with. So the answer is you need 8.0 grams of sodium nitrate to make 1.5 grams of oxygen. So that's your basic setup for stoichiometry, and you need to be able to create, this table, know how to figure out all the parts. Remember that you always have to go through the moles and the mole ratios. You do not do proportions with grams, you only can do proportions with moles and mole ratio in order to figure out these problems. It gets a little more complicated when we're talking about the limiting reactants or the limiting reagents. In this case, we have a problem that says if you combine aluminum with oxygen, you get aluminum oxide. And so if you have 7.42 grams of aluminum and 6.42 grams of oxygen, which one of those is limiting? Which one of those are you going to run out of first in making this reaction of aluminum oxide? And this problem may also ask you to go on to figure out how much aluminum oxide would be made when you have these two amounts. So to figure out the limiting reagent or limiting reactant, again, you set up your stoichiometry table here. We are going to be comparing aluminum and oxygen, and we look at our balanced chemical equation and see that our mole ratio says that's 4:3. Our molar mass, if you go and look that up again, of course, oxygen is 32, aluminum is 27. And then we've got some gram values. Now here, one of these gram values is not going to be enough. And so we're just going to pick one and work with it. So we'll just start with the aluminum since it's first in line. So let's say aluminum, if it's 7 grams, 7.42 grams of aluminum, then we're going to be solving for how much oxygen that would require and see how it compares to how much oxygen we actually have. So 7.42 grams times our molar mass, which is, 1 mole has 27 grams in it. And again, you can set up your problems this way, or you can divide by 27, whatever is best in your mind to remember how this works. But if you do this problem, you will see that you've got 0.275 moles in your 7.42 grams. So that's the same thing as 2.75 moles. So if you have 0.275 moles of aluminum, then you want to figure out how many moles of oxygen are required in a proportion that is 4:3. So you use your mole ratio, and so what I'm going to put, since I'm looking for oxygen, I'm going to put that on the top. I'm going to say the relationship is 3 oxygen to every 4 aluminum, and that is proportional to this unknown amount of oxygen to this 0.275 moles of aluminum. So I'm looking here, trying to find the moles by setting up a fraction that are proportional, equivalent fractions using the mole ratios. If I go and solve for x, then I see that x will give me, I need to have 0.206 moles. That's how much oxygen I need in moles. And so we'll put that in here, 0.206. And then we see, well, what does that give me for how much oxygen is required in grams? So that would be taking the 0.206 and multiplying it up here times 32 grams per mole. That x means times. And so if you do that multiplication, you'll see that you need 6.6 grams. So at this point, you go back and see how does that compare to what you actually have. If you need 6.6 and you have 6.42, well, obviously you don't have enough oxygen. So oxygen is going to be your limiting reactant. It is going to run out before you have used up all of the aluminum to make your aluminum oxide. So what if your problem asked you to calculate how much aluminum oxide would then be produced by that or 6.42 grams of oxygen. So then we've got to do another stoichiometry problem where you're going to have to recreate this column with the new values. So really we don't have 6.6 here, we've got 6.42. You'd have to calculate a new mole value to use that to then determine, using stoichiometry, how much aluminum oxide needs to be produced. So if you've got a two-step problem, then once you figure out which is the limiting reactant, make sure that you use the value from that limiting reactant, not the value that you've calculated when you're trying to do the comparison to do the second half of the stoichiometry problem. I'm not going to do that now. You could just turn back a slide and see how stoichiometry happens, because really it's the same procedure. You just need to make sure you're using the correct values when you go to do it. You will also need to calculate some empirical or molecular formulas given the percentage decomposition results or the gram decomposition results. And so there was a little rhyme that I used in the video that said percent to grams, mass to mole, divide by small, multiply till whole, as a way of keeping track of your steps for doing empirical formulas. So with percent to mass, you just take the percentages and turn them directly into grams, because you'll see that both of the percentages, 68.4% chromium and 31.6% oxygen, are both, they'll add up to 100. So we can say that we had 68.4 grams of chromium and 31.6 grams of oxygen. So percent to grams. Then we go from the mass to the moles, and just do that by either multiplying or dividing. Either set up factor label analysis, or it's easier for me to think about dividing by what the molar mass is. So oxygen is 16 grams per mole, chromium is 52 grams per mole. So when you do the multiplication, of course, mole ends up on top. So that this says that we have 1.32 moles of chromium and 1.98 moles of oxygen. So that's the mass to mole. Now we divide by small. Obviously 1.32 is the smaller number here. So we divide by that smaller number. And if you divide with moles, then you get rid of your units and you're just left with values. This will give us 1, and this gives you 1.5, and then it's multiply till whole. So we don't want any fractions. We want to multiply till we get whole numbers. So if we multiply both by 2, then we're going to get whole numbers of 2 and 3. So the 2 corresponds to the chromium, so it is Cr2, and then the 3 is the oxygen, O3. So the formula, the empirical formula for this compound is Cr2O3, given the percentage data that you have been handed. If you are asked to give a molecular formula as the second step after you've figured out empirical formulas, then you'll be given a molar mass. And so say you were given a molar mass of 504 grams for this compound, then you need to calculate, well, what is the molar mass or the molecular mass in AMUs? Just you can jump back and forth between the atomic mass in AMUs and grams. But you go back to the periodic table and add up all of these individual atoms and see that this comes to 252 grams per mole, or AMUs, representing the mass of this particular molecule. And you compare that number, 252, to 504, and what's the relationship between it? Well, obviously 504 is twice 252. So this empirical formula needs to be doubled. It's twice as many atoms present in the molecular formula. So we would just say Cr4O6, using the molecular mass or the molar mass as a way of figuring out what the exact molecular formula is. So you do need to be able to do that second step, which happens after you've figured out the empirical formula. You will need to answer a few questions on wavelength. Remember how to identify the parts of the wave, that we have the peak or the crest here on the top and the trough on the bottom, and that a wavelength is from one point to that same point on the next wave. So we've got crest to crest, or trough to trough, or you can go from a node, we're starting in sort of a downward direction, go all the way through till we start in that downward direction again. All three of those will be a measurement of a wavelength, and all three would be the exact same amount. The frequency is how close these peaks or troughs are together, how fast the wavelengths pass by any one particular part, any one particular space as you're sitting there watching them. And you'll need to work with wavelength, frequency, and energy relationships using those two very important formulas that tell you that the speed of the wave is equal to the wavelength times the frequency, how long any particular wavelength is, times how fast it moves, tells you the speed. And from this relationship, you can see that if wavelength increases, then frequency has to decrease to give you the same speed. And we're dealing with light, where all of the wavelengths and frequencies will all have the same speed. Energy relationship, that was the relationship between the frequency and the energy, and it goes with a constant, Planck's constant. You don't have to memorize Planck's constant or the speed of light, what c equals, but you do need to know these two formulas and be able to use them in problems. You'll need to know a little bit about the emission spectra of atoms and how that can be shown as a bright line spectrum. Remember, that is when an electron is energized, so it moves out an orbital. Here we've got the nucleus of the atom, and our little electron, normally resides here, and it'll be bumped out when energy comes in. And then when it gives off energy, it will then jump back to its own ground state, preferred orbital, and it releases energy as a photon of light. And the smaller the jumps, the lower the frequency, the lower the energy of the light that's released. So red would be released for smaller jumps, and blue light would be released for larger jumps. You also will be asked to just identify what element is shown by a particular emission spectra given some data. So if you've done the worksheet that we had in class, I think you'll be set on that one. You also need to write electron configurations. So if I add in either the expanded or the noble gas style, so if I ask you to write the electron configuration for magnesium, going back to the periodic table and counting up all the electrons before you get to the block that contains the atomic symbol for magnesium, you will see that it has 1 s2 electrons, 2 s2, 2 p6, and then 3 s2. You're done. You're sitting on magnesium. If we were to put this in the noble gas shortcut, you'd go back to say what noble gas fulfills this configuration. Well, that would be neon. So magnesium looks just like neon, except it has the 3s2 electrons. And remember, these are our valence electrons. They are the ones that become very important when it comes to drawing Lewis diagrams. As in Lewis diagrams, you just want to show what electrons are found in the valence orbital. So with the Lewis diagrams, we just need to know how these valence electrons are arranged. So let's say, we'll say nitrogen, and nitrogen has 5 valence electrons. You start and go around like the points of a compass, and then you start doubling up. So it doesn't matter so much where you start, as long as when you're done drawing me nitrogen, you've got 3 spaces where the electrons are all by themselves. And then we're going to combine this with something. Let's combine it with bromine, one of those halogens, which has 7 valence electrons. And so you can show me how they are arranged again. 3 are already paired, 1 is all alone. And then when it comes to the actual molecule, you can go ahead and draw lines if you want to save on drawing all those dots for the actual bonds. But then be sure to put in all of the lone pairs of electrons on the individual atoms. And so I'll be looking for something like this when I ask you to draw me the compound, showing the Lewis structure for this nitrogen tribromide molecule. So that covers what you need to study for the test, and I think if you are feeling comfortable with this, and especially with those math calculations and stoichiometry, you'll be set to take the second quarterly test.